I taught here at UCLA for 11 years. I have many old friends here, some of which I've been able to catch up on, and it's been a great pleasure. I'm going to be talking about work that was done in collaboration with Monica Krishan, was a postdoc, and Ye Lu, a visitor from China, and Riley Miller and Peter Latham. Peters at the Riley was an undergraduate at Princeton, and Peters at the Gatsby. Peter, when I get into some of the mathematical heavy lifting, that's where Peter comes begins to do the heavy lifting. I once said to him, I said, Peter, you do integrals. I don't do integrals. But since then, I've started doing Bayesian stuff, and if you're doing Bayesian stuff, you got to do integrals. But I only do very amateurish integrals compared to what Peter does. This work, which is primarily a modeling work, is constructed on the basis of research results that Monica and Ye Lu and I obtained actually about 3-4 years ago now. And at the time, it's an extremely simple experiment, as you'll see. I kept telling Monica, I said, look, I don't work in this area. You can't trust me on the literature. Someone must have done this before. It's an unbelievably simple experiment. We never could find it, so then we submitted it for publication, and eventually through a lot of critical reviews, we found it. Indeed, someone had once done this before. As near as we can tell, it's only been done once before. And fortunately, they got exactly the same results that we did. Even though it was run in the pre-computer age, so it was run by it's conceptually exactly the same experiment, but run with a different technology. So the guy who ran it first was Robinson. It was his PhD dissertation at Michigan, and this was a pre-computer or early days computer. Some of his data, he says, were on punch cards. Reminds some of us of those days. But his basic data he obtained from this apparatus. So the subject was sitting at this apparatus, and they had this very low friction lever, just enough friction to stay where you put it, which they could move at will, and they were watching alternate flashing lights either on the left or the right, and they were to adjust the lever to indicate their current perception of the probability of a flash on the right. So they're watching a Bernoulli process, and they're estimating the parameter of this Bernoulli process. And it's a non-stationary Bernoulli process. That is, they're told that the probability of a flash on the right may change from time to time, but they're not told by how much it'll change or how often it will change and so on. In Robinson's experiment, the contingencies on change were actually quite different from ours, but all the important results are very similar to ours. And so the subjects in Robinson's experiment just tried to track what they took to be the Bernoulli probability for this flashing light. Everybody clear about that? Feel free to interrupt at any time. Yeah?
You were told that the probability that events are independent. This is what we're saying, that it's a Bernoulli process, so the events are independent. It's not about lack of chain of events. So the fact that you just saw one color does not...
That's right. There are no sequential dependencies, right? The only thing that happens is that there are step changes in the underlying, the hidden parameter.
And the subjects know this.
And the subjects know this. They know that they can expect their changes, but they don't know anything about how frequent those changes might be, nor how big they might be. And that was true in both the Robinson experiment and in our version of the same experiment. And he recorded the lever positions on a chart recorder. And here you see a reproduction of one of his figures. And it has shows very clearly the first interesting result, which is the subjects are not moving the lever on every observation. Now, Bernoulli process is interesting in that the outcomes can either be 0 or 1. Those are the only possible outcomes, but the underlying parameter is usually somewhere in between. So the Bernoulli process, you're getting jerked around by the outcomes a lot in estimating the parameters if you do it in the usual way, which is as a running average. Usually most models of this kind of thing are an exponentially decaying running average of what you've seen over the past. And when you apply such a process, the value of that average gets jerked around essentially on every trial for reasons that I hope are obvious. But the subject's percept, at least judging by how they set the lever, doesn't get jerked around. The lever stays in one place for some number of trials. And this is showing a record from one of the step transitions in the true probability. So the true probability step, this is the true probability. Right? The subject had the lever fairly close to what the true probability was. It took some number of trials before the subject detected the change, during which he made one small adjustment in the, if you like, the wrong direction, right? Because he hadn't yet detected the change. Then you see a very large, that's another interesting thing, a very large movement of the lever, and then some small movements that converge on this. But because this is a transition record, you don't get to see the fact that the lever can actually stay unmoved for quite some number of trials, both in his experiment and in our version of it. So, two interesting things at this point. There isn't a trial by, at least on the behavioral output, there isn't a trial by trial adjustment in the percept of the hidden Bernoulli parameter. And the percept can undergo very large changes in the span of a single trial. Both of these are substantial constraints on a viable underlying model of the process, a computational model of the perceptual process, which is where I'm headed with this. Our version of this is, of course, done on a computer screen. The subjects are sitting at a computer. There's a box of rings. Every time they click on the next key, a green or a red circle emerges from the box. You can think of it as an urn. And they have this slider there, which they can move with the mouse, and that's the equivalent of Robinson's lever. And we ask them to set the slider to indicate their current perception of the probability of a green ring. And again, they're told that it may change. The box may be silently replaced at some occasions. And when they believe it has been changed, they're asked to click on this button here that says the box has changed. So we got explicit. Robinson didn't explicitly ask his subjects to say that they thought there had been a change, but we did. And when we debriefed the first 5 subjects, they all spontaneously reported that they all said something like the following. You know, sometimes when I said there was a change, later on, after I saw more rings, I decided there hadn't been a change. So they had second thoughts. All right? So at that point, when Monica told me about that, I said, ooh, that's important. So we added a button called I Take That Back. So when you had a second thought, you could click on that button. You weren't allowed to go back and say, and I want to readjust my earlier slider positions, right? But you just reported that, you know, I've had a second thought here. The true p-value changed in steps of varying but rather large size. Steps were considerably smaller than ours. The changes were completely unpredictable. They were scheduled by a geometric approximation to an exponential distribution. And the probability of a change on any one trial was quite low, 0.005, which means that the expected number of trials between changes was 200 trials. Okay. However, geometric processes are very random, right? So there were occasions on which a given p-value only lasted for one trial. Of course, it's in principle undetectable that there should have been a change. And there were also occasions when the p-value remained the same for hundreds of trials. As I've already indicated, the subjects were told that there would be changes, but not how many. Our results look, our slider positions look exactly like Robinson's lever settings. Here is a, trust me, entirely representative slider setting. The dashed line is the true underlying hidden p-value, which you see underwent a very large but short-lived change at this point, and then back and so on. And the solid line is the trial-by-trial slider setting. And as you can see, the subject is tracking the hidden value of the parameter fairly well. You can see that the slider can undergo practically a full range change in the span of a single trial. So the estimate of the p-value, the hidden p-value, can change by huge amounts in the span of a single trial. And you can see that the slider can go for quite a number of trials. Here it's that's 40 or 50 trials without moving at all. So they judging at least by the slider setting, and I know what some of you are thinking, and I'll get there in a moment, but judging by the slider setting, the percept doesn't change in the face of the stochastic fluctuations in the Bernoulli process. Something that may come as a surprise for those of you familiar with the Kahneman and Tversky work, but which is actually not inconsistent with a very substantial literature, is that our subjects are, in general, are quite accurate over the entire range. So here I'm plotting the median. I've just tossed together all the slider settings. So, I forgot to say, there were 1,000 circles per session, and each subject ran 10 sessions. So we have 10,000 slider settings from each of 10 subjects. I'm a psychophysicist, so we like to work with lots of data. And I'm just tossing together all these. We did not program the p-values. I mean, there was a computer that was randomly deciding on them, but we had no direct control over it. But between the subjects, you spanned a whole range of p-values. And all I'm doing is showing you the median and interquartile interval of the slider settings as a function of the true underlying p-value. And you'll seldom see a better identity function with empirical data than that. And the same is true for the precision of the estimates, so that you can ask two different things about this. First of all, are they on average accurate? The answer is yes. And the second question you can ask is how close are they to how close is the slider setting, on average, obviously, to what it should be. Now, there's a huge issue about what it should be. It shouldn't be the underlying p-value, right? Only God knows what the underlying, or somebody, but only the computer knows what the underlying p-value is, right? So the underlying p-value may be 0.5, but you've seen 6 green circles and 4 red circles in the last 10, right? So they're on the evidence, the p-value isn't 0.5, right? So there's a huge issue about to what do you compare the slider setting, right? And part of the reason this experiment was doable is that in the last decade, people have worked out Bayesian ideal probability trackers, and Peter Latham was one of the people that worked it out. So we use as our standard of what the subject should be doing the p-value that the Bayesian ideal probability tracker would assign given if it had seen the data that the subject has seen. So we compare the slider setting to that. And if you think about it a bit, I hope it's intuitively obvious that differences in p-values are not the same in different places on the scale. That is, I hope it's intuitively obvious that the difference between 0.5 and 0.6 is smaller than the difference between, let's say, 0.87 and 0.97, right? They're both 0.1 delta p, but the one near the extremes is much more readily detectable than, that is, that difference is much more readily detectable than one in the middle of the p scale. And there's an information theoretic measure of exactly that called the Kullback-Leibler divergence that measures how far apart two distributions are. So that's the appropriate measure to use in assessing how precise subjects are, not the actual p difference, but the Kullback-Leibler divergence between the setting that the slider setting and the ideal Bayesian observer. And there are actually 5 different cumulative distributions plotted there, but they all fall on top of each other, and that's sort of the point. Namely, this is the cumulative distributions of the Kullback-Leibler divergence for bins at different places along the p-axis. So you've got one bin in the middle, you've got bins out here in the extremes. You're binning the data and asking, well, when they're estimating p-values out here at the extremes, how precise are they using the Kullback-Leibler divergence? And when they're estimating p-values in the middle, how precise are they? And it turns out they're equally precise regardless of where they are in the range. Does anyone want to? I realize that's a bit technical. If you want to ask questions about that, now's a good time to do it. I'm sorry?
So you mentioned that this.
Yes, well, so most of the, this is not as unusual as you may think in the sense that there's quite a substantial literature on the direct estimation of probabilities as opposed to making bets or making reverse probability estimates. Almost all the Kahneman-Tversky kind of literature is either inferring what the underlying probability must be from the kinds of bets that people are willing to make, or they are reverse probability judgments. I'm not sure how many people are familiar with the
They're not perceptions that
Yeah.
are the degree to which the probability has an impact on the choice. So how much the probability gets weighted on choice.
Yes, that's one aspect of it and so on. I mean, they don't come from experiments like this when you just flat out ask people, what do you see, or what's your perception? There is a substantial literature, not on a trial by trial basis, but usually on some number of trials, that shows basically just what we're showing here, which is what Robinson, by the way, found. Robinson commented on the same thing. He says, in my data, subjects are accurate over the whole range. So the subjects make quick and accurate responses to change. We're looking now at 2 sorts of things. You can look at just what does the slider say independent of what the subject says, and they don't always agree. Subjects would sometimes seem to clearly recognize that there had been a change by making a big slider movement, and yet not say, we thought maybe they were absent-minded, because sometimes a couple trials later they'd say, oh, and I detect a change. Anyway, there wasn't perfect accord between what the subjects were doing with the slider and their clicking on the change button, so we scored, we looked at changes in 2 ways. The one that Robinson used, which was just how many trials elapsed. If you remember that first Robinson plot, you have the step change, and then 5, 6, 7, 8 trials later, you have a step change in the slider. So that's one way of getting how many trials, how much data do you have to see, and before you recognize there's been a change. And of course, the other thing we can look at is there's a step change, and then some trials later, the subject clicks on the, I think the box has changed button, right? And I apologize a bit for the complexity of the figures here, but I'm trying to save time by combining showing you the data with showing you how the model does. So part of what's on both of these graphs are not just the data, but how well our model of the data is doing. And it looks a little blurry for some reason. I don't know that, but if we can adjust the projector. But this is the distribution. There are 10 subjects, okay? And this is the cumulative distribution across subjects. So there are 10 steps in this cumulative distribution of the median number of trials to detect a change. So based on the slider. And so you see it was roughly 10 trials to detect it. And this is the distribution of the first quartile of detect. So each subject, remember, each subject saw 10,000 of these things, and each subject saw roughly 100 changes. So we have a lot of data from each subject, and we can look at the distribution of their change latencies. And so you have a first quartile of each subject's distribution, the median, the third quartile of each subject. And then here what I'm plotting to summarize across subjects, because there are non-trivial differences between the subjects, I'm plotting those statistics. So this is the cumulative distribution of the subjects' medians. This is the cumulative distribution of their first quartiles. This is the cumulative distribution of their third quartiles. And the lines here are how well the model does when on the same, so the model generates distributions. The model behaves exactly like the subjects. That is, it generates slider settings, simulated slider settings on every trial. And you can compare how, and the model records changes. The model has an explicit change detection algorithm built into it. So you get how long it takes the model to detect changes, and that's what we're looking at here. Now, of course, the other thing you want to know is, well, how many false alarms, you know, how, are they, the subjects detecting most of the changes? And yeah, the answer is, so the black symbols are the subjects, and this is an ROC space. This is the hit rate, and this is the false alarm rate. And you can see that subjects, this subject, for example, detected every single change. Whereas the subjects are all up here around 90%, except for one not so good subject down here at about 65%. But they're detecting most of the changes. And of course, one way you could do that is just to say there was a change on every trial, right? So you have to look at the false alarm rate. And as you see, the false alarm rate is very low. So they're detecting most of the changes, and they fairly rarely say there's a change when there in fact has not been a change. Yes?
Is there, that means they detect the change before the changes again, not that they did it right afterwards.
Exactly. No, exactly. There's no way if they could do it right afterwards, something's wrong, right? Because
That varies a lot. Right?
that varies a lot depending partly on the size of the change. Remember, some changes were much bigger than others. And of course, the bigger changes are more readily detectable than the small changes. Yes, Frank?
I might be confused. When you say the model does the same as the subjects, both of them must have a criterion they use to decide when they really think there's a change. And that,
Yeah. They have to have
so,
decisions.
so the point is, the model is fitting because you set the model's criterion to be the same.
The model
as
has
the subject.
3 parameters,
Yeah, okay.
a decision criteria. It has 2 of them, just 2.
Okay.
But of course, decisions require criteria. Then this is a decision. So
Yeah, okay.
for sure, there are decision criteria, but there are only 2 of them. We'll come to them in a moment. And the colored symbols are the model. And with, so it's too technical about, as you can imagine, you know, how you go about adjusting the parameters on the model and so on. But I hope spend some time on the parameters when I get there in a moment. But what you should take away from this is under reasonable settings of the model parameters and the same settings that generate the other fits. You're fitting the model, you're fitting to many different aspects of the data, right? And they're incommensurable. There's no way to say you have, so there's a issue about just how to fit. But what you take away from this is that the model is getting very similar hit rates and false alarm rates when fed the same data. That's all that one wants from that. And finally, the subjects have second thoughts, and here's the cumulative distribution of the latencies to the second thoughts. So the latency is you say there was a change, and then you see some number of additional trials, and you say, you know, I think I was wrong. So it's the number of trials between when you said there was a change and when you click on the, I take that back. And as you can see, most of the second thoughts, as you might anticipate, occur within 20 to 40 trials, something like 95% of all the second thoughts. But there's a very long tail. Sometimes, you know, 250 trials later, they say, you know, I don't think there was a change. And the model does a reasonable job. It doesn't have quite as long a tail, but the model has second thoughts after more than 100 trials sometimes. And so it's It's not a terrible approximation to what the subjects are actually doing. Okay, so now we come into the, so from here on in we're into the modeling full time. That's the data. And now the question is, what are we to make of this? Now, I bet anything, Frank and several other people are thinking, well, they don't move the slider because they're lazy, right? They actually think it's changed, but you know, it's a bit of a nuisance to use that mouse and move the slider and so on. So they only move the slider when the discrepancy between their current percept, keep in mind the slider setting in effect tells you what your past percept was. And so you might be saying, well, let's let it ride even though I think it's actually a little higher. But when it gets too much higher or too much lower, then you move the slider setting. Everybody on board with that?
Higher and lower meaning higher and lower rates.
Probability. So suppose you got it set at 0.3, right? And you know, you kind of starting to think, well, you know, maybe it's 0.34, but you think, that's chicken shit, right? I'm not going to move the slider for that little difference. But when it gets to 0.4, then you say, oh, okay, I'll move the slider. That's intuitively the idea. Okay. So in slightly more formal terms, that says the subjects have a threshold on their output, right? They have an underlies the performance competence distinction, which is at the core of psychology in some ways. You know, the subjects have an underlying percept, but it isn't really mapping faithfully into the observed slider setting because of this laziness, because they're putting a threshold on the output. So virtually everybody I've ever told this about, that's their first idea. And it was our first idea, but that can't possibly be the case because it has a very clear prediction about the form of the joint distribution between step widths and step heights. So I'm now talking about the steps in the slider setting, right? So keep in mind the kind of record we're looking at. Slider setting goes along, same, no change, no change, no change, little change, no change, no change, big change, okay? So those are the steps. And for each step, you can measure how wide it was, how many trials went by before the change, and the height of the change, right? And you can plot the joint distribution of step width on a log scale because the widths run, sometimes there's only one trial and sometimes there are hundreds. So we're plotting the step widths on a log scale here and the step heights on an ordinary scale. So this is delta p, and this is how long the slider went before the change, the delta p. And these are the marginal distributions, right? Just the collapsing the joint distribution onto either axis. Now, if there's a threshold on the output, what does that mean? It means you don't make small slider movements, right? It should create a hole in the marginal distribution of step heights. But in fact, tiny movements of the slider are the most, as you can see by looking at the marginal distribution, they're actually the most common kind of thing. So the subjects are not even faintly reluctant to make very small adjustments in the height of in the slider setting. In fact, that's the most common kind of adjustment. So then we set out to try to model this. Well, there have been several models of this, not usually the non-stationary, well, some of non-stationary as well, but closely related phenomena. And they've all been running average models, exponential running average models. I'm pretty sure Frank has done more than one running average model in his modeling efforts. Is everybody clear about what the running average is? You know, you're averaging over some number of previous trials. You can do it in various ways. You can have a fixed window and you only look at the last 10 trials or the last 20 trials. Or most commonly what you do is weight. The farther back in the past a trial is, the less weight it gets. It's a very attractive kind of model because it's path independent. You don't actually have to keep track of the previous observations. All you need to do is keep track of the mean. That is, all you need to know is what the mean was on the previous trial in order to update on the current trial. You don't need to know what happened before. Anyway. Such models can be made to track a varying probability. If they are averaging over quite a number of trials, then they track slowly. I hope this is intuitively obvious. That is, when the probability changes, the average goes down slowly because it's averaging over quite a number of trials, and therefore it's averaging together the trials before the change and the trials after the change. The advantage of averaging over quite a number of trials is that you get a better estimate. It's less jerked around by the stochastic properties of the sequence you're looking at. But the disadvantage is that it adjusts slowly. You can make a short average, in which case it'll adjust quite quickly, but then it's very noisy. It tracks the noise. It gets jerked around a lot because it's not averaging over very many of the data. Now, none of these models actually detects change. You have to distinguish between tracking change and detecting change, right? So the running average thing tracks the change more or less, but it doesn't detect it. There's no machinery in there. You couldn't interrogate it and say, well, when did the change occur? Because it doesn't know from nothing about the changes. It just tracks things. So our subjects are clearly detecting the changes. So how do you adjust such a model in order to detect changes? Well, one idea that occurs to, it didn't take long. I've tried this on 4 or 5 people who were kind of into this kind of modeling, and almost everybody comes up with the same model within about 10 minutes. They say, well, look, what if we had 2 running averages, one slow and one fast, right? So if there's no change, they will approximately agree, right? Whereas if there has just been a change, the fast one will be adjusting to the change rapidly, whereas the slow one won't, and therefore they will diverge, and you can put a threshold on their divergence, and you call a change when it exceeds some threshold. So we ran that model, and no matter what you do, you can't get rid of the whole. So this is a 2 running average model with explicit change detection, but no second thoughts. But no matter what you do, you can't get rid of the hole in the marginal distribution of the step heights. One of the reviewers said, well, what if you had a stochastic threshold? Okay, come on, guys. All that's going to do is round off the edges, right? Think, right? But we ran stochastic thresholds, so now you have 5 free parameters, right? Because you have parameters for the stochasticity. This is actually with the stochastic threshold. Yes, Frank?
So again, I may not understand something, but isn't it a model just to say this is an ideal Bayesian observer?
Well, so the models that we used as our reference things, but they don't detect changes. They're Bayesian trackers, but they don't detect changes. That is, they're much better than running average models at adjusting to changes, but they don't. You'd have to put in.
Throw that in.
You got to throw that in. The reason we didn't is because the ideal Bayesian tracker, just like the running average, will adjust its estimate on every trial by a non-trivial amount. That's inherent in tracking a Bernoulli process with a Bayesian estimator, and the subjects aren't doing that. Yeah.
Since you're asking them questions about when do you think it changed, do you think you got it right, and so on, if you make your Bayesian model do that too.
You can certainly make a Bayesian. In fact, part of our model is a Bayesian change detector.
Never mind.
Yeah, okay. So part of our model is a Bayesian change detector, okay? I haven't gotten there, but I'm headed there, okay? But a simple Bayesian probability tracker won't the biggest problem is that it won't reproduce the distribution of step widths and step heights. That's a huge, if you don't carry away anything else, one of the empirical claims is that that distribution is a very powerful constraint on viable models. That if you think it's easy to duplicate that distribution, be my guest. Yes, Alan.
I don't know if this is the point to introduce this idea, but there's a Gracian issue here in the sense that you wouldn't describe the system to the subjects as there will be changes. I'm imagining what the subject is implicitly thinking. You wouldn't, the subject is thinking, well, when they say changes, they mean changes worth mentioning. They don't mean a change in the probability between between 0.7356 and 0.7357, because that's not worth mentioning. So
Would take about 1,500 trials. If you calculate the Kullback-Leibler divergence, it would take 1,500 trials to detect
no,
that
but
change.
they're not thinking about
Yeah.
that. They're thinking in a Gracian way. When you say there will be
Right.
changes, they're assuming changes of a
Detectable
magnitude
kind.
well,
I
not
think
even
that's-
detectable,
yeah.
of a size worth mentioning, because they're not mathematicians.
Right.
They're saying, why would he tell me this unless
Right.
the changes were of a certain size?
Yes.
Otherwise, it
I
would
think
be
you're absolutely right.
problematic. So they're assuming that there's
And a certain frequency. I'm going to show you data
Right.
that they actually started out thinking the changes were more frequent than they actually were.
right.
Yeah.
So there's an assumption that they in their interpretation of the instructions.
Absolutely.
That there will be a certain frequency and a certain size of the things.
Absolutely.
That there won't be very small ones.
Right.
And they won't be super infrequent.
Right.
So how does that, I mean, when you're modeling this, if you're trying to model animal behavior in general.
Yeah.
there's-
These are humans, but
But, right, but if
Okay,
you're trying to
yeah.
say that this might tell us something about, not just human species.
yeah.
You have a problem in the sense that the instructions themselves are being interpreted within a social, what I'm calling the Gracian constraints
Yeah.
of
Yeah.
relevance.
All of that I think is true. Yeah.
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 So that suggests that the subjects would, you're asking, why don't they make a change every time? I mean, one of your questions is, and I'm saying, one of the reasons is that they are assuming that there won't be little teeny weeny changes.
But I just showed you that that's false.
So why, if that's the case, why do they do that?
Well, this is so.
Because they don't
Bear
want
with
to
me a
be
moment.
being too
Bear
far
with
off.
me, and I hope that the answer will become clear as we get a little further into the model. Basically, to anticipate, it's because they only adjust the slider when a very simple calculation tells them that they've got a problem, that their current estimate is not congruent with what they've been seeing. At that point, they have to figure out why they've got a problem. There's where the Bayesian change detection comes in. One reason they can have a problem is that their original estimate was based on a very small sample, and so there's just small sample error, in which case you're going to make small corrections, right? A different reason why they have a problem is because there's been another change in the hidden probability since the last one, right? And yet a third one, this is where the second thoughts come in, is that they were suckered by a garden path on the previous change detection, so that's what threw them off. And the problem is that they should get rid of the earlier, the previous, right? So the model says that that's what they're doing, okay? The small adjustments come from the adjustment in the estimate based on the thing, I've seen more data and I've got a better estimate. And that's very common. Remember that actual changes are quite rare, and the subjects only rarely detect actual changes. Most of the slider adjustments are just improving their estimate in the absence of any evidence that there's been a change. Okay. Does that speak to your question? Okay. So why the steps? So the steps play. So here's the big picture that I was just elaborating on, right? Here's a big idea behind this model. The big idea is that the current percept that you have of what the probability is at the moment is actually a byproduct of your constructing a large-scale model of how this process is behaving. Right? So what you're really focusing on is detecting the changes, because as an information engineer would tell you, if you've accurately assessed the changes, then you can calculate the current value anytime you want. So the idea is they're building a model of the experienced sequence in terms of its change points. Now a change point is takes two numbers, right? In slightly more technical language, it's a 2D vector. Right? What exactly those numbers refer to depends a little bit on what you choose. But one sensible thing is that one number refers to the trial number at which the change occurred, and the other number refers to the probability after the change. Right? That's one way of parceling out the two numbers. Another way is simply the one number refers to the trial at which the change is estimated to have occurred, because you don't know when the change occurred, you have to estimate it from the data. And the other number is the cumulative number of green circles that you'd seen up to that point. The model is completely agnostic about which one of those it might be using. One of the things I want to stress is that this kind of change point representation gives you a surprisingly economical and accurate characterization of the data that you observed. And what I'm heading toward here, for those of you familiar with this kind of thing, is what's called a minimum description length idea. The idea is that you're trying to describe your past experience with as few parameters as possible, all right? But there's inherently a trade-off between the number of parameters, the description length, and the accuracy of the description. But what I'm showing here is, in effect, if this was an introduction class at minimum description, yes. So there's one change point, there's another change point, there's a third one, there's a fourth, this one doesn't count, that's the 0, 0 one. So there's 1, 2, 3, 4 change points. This is a sequence of 1,000 circles. The black lines, the blurriness is screwing this up a bit, but the black lines is the cumulative record of the stimuli, not the subject's response. You imagine a chart recorder that's going along, and every time there's a green circle, it steps up 1, okay? So that gives you the cumulative record of the number of green circles that the subject has seen. And if you think about it for a moment, you realize, oh yeah, the slope of a cumulative record is the rate, right? It's the number divided by time. That's the beauty of cumulative records, is that they show you the rate without any averaging. So there's no smoothing in these cumulative. So when the rate changes, you see this abrupt, there's no smoothing, you see this abrupt elbow in the black line. So the black line is the actual stimulus sequence, and the pink dashed line connecting those circles, good, someone sharpened up the focus. The pink dashed line is just the line connecting the circles. Well, the take-home message is that the black line's right on top of the pink. The pink line's doing a really good job of representing the actual stimulus sequence. But the stimulus sequence had 1,000 observations, and the pink representation of it has 4 2D vectors. So you're replacing 1,000 numbers with 8 numbers, and that's what economical description is. That's the name of the game. That's a minimum description. So the point of the slide is that this change point, if you calculate the change points, you get a very compact yet very accurate representation of the sequence that you've actually experienced. So this is the model. Sorry, I'm misjudging my time a bit here. I'll try to rush to an end here as fast as I can. So this is the full-blown model. It's basically a 2-stage model. And the first stage is what we call, if it ain't broke, don't fix it principle. If you've got a percept that seems to be doing a fine job of representing the world, don't take the trouble to mess with it. All right? So if you have a probability estimate and it seems to be doing a pretty good job of predicting how many green circles you've been seeing, then you leave it alone. This can be reduced to an extremely, the appeal to this is that it looks hairy, but in fact it's a completely trivial calculation. It uses the Kullback-Leibler divergence, which sounds fancy, but is in fact a very simple calculation. And this tells you whether you've got a problem. And a huge point is, most of the time, you don't have a problem. And if you don't have a problem, you're done. You don't have to do any more computing, any more estimating. So all you're doing is comparing on a trial-by-trial basis your current percept against the observations that you're seeing, and you ask first, do I have a problem? If the answer is you got no problem. So that's the first decision criterion, Frank, is the decision criterion on the do I have a problem. And the second stage only kicks in when the answer is yes, I've got a problem. And now I'm going to be repeating what I just said to Alan a moment ago. Okay, so now the question is, well, why do I have a problem? What's giving me this problem, right? So the first question you can ask is, okay, the sequence that I've looked at since the last change estimate, is that better represented by a single p-value, in which case there's been no change? In which case my problem is just that I had a small sample estimate, right? I misestimated the p-value because I didn't have much data. And the solution is just, adjust your estimate on the light of the additional data that you have. The alternative is that no, there's been another change, that this sequence is better described by a model that has 3 parameters, a p-value before the change, an estimated point of change, and a p-value after the change. Okay, so you're pitting a 1-parameter model, the no-change model, against a 3-parameter model. Is there any Bayesians in the room here? So the great appeal of the Bayesian formalism is that it naturally and from first principles deals with the issue that you're staring at here, namely that a 3-parameter model will always be better than a 1-parameter model, right? Unless you do something to take into account the complexity of the model, the more complex model will always be a more accurate model than the less complex model. And of course, in traditional statistics, there are various quite ad hoc ways of trying to take that into account. But one of the great appeals of Bayesian statistical inference is that there's nothing ad hoc about it. It's automatically taken into account by the diffusion of the prior, which I can explain more about in the discussion. I don't want to get into that now. So the algorithm does a Bayesian model comparison at this point. That is, it looks at the 1-parameter model versus the 3-parameter model, and it decides which is a better model of the data. And whatever that decision is, determines the adjustment that it makes. But if with one caveat, if the it considers one further possibility, which is what I mentioned before, namely that your problem is the last change point. Then you shouldn't have added the last change point, that if you look at the data that goes back to the penultimate change point, the best model is actually a no-change model that goes all the way back to the penultimate change point. That's, of course, where you get second thoughts, right? When it turns out that the best model is the one that goes back to the penultimate change point, then you expunge that last change point from your representation that you're building, and now you have a simpler and better model as a result of your second thoughts. Yes?
So, why doesn't though, and I confess that I only partially grasp what you just said. Well,
Sure, you've got lots of company. Yeah.
why doesn't it all unravel if that's the case? if the penultimate one is better than
Right.
the most recent, well, then the one before that would have
Yes,
been.
yes. The model actually allows you to do that. The basic answer is it just doesn't happen. It never unravels. The algorithm always finds a good model, and it never unravels. The pink lines that I showed you were actually generated by this model. And had I taken out the second thoughts, there would have been a considerable number of additional change points in the record, right? So the second thoughts do delete change points, but it never unravels all the way back. I understand that in some sense that's not you'd like a more principled explanation of why it doesn't unravel, and I'm afraid I can't give you one. I mean, just tell you empirically it doesn't happen. Okay, so what the Bayesian is doing here is implementing what's sometimes called Einstein's razor, which is a version of Occam's razor. Einstein supposedly said, I've looked up what he actually said, and as usual, this is not what he actually said, but what he supposedly said is that we want our theories to be as simple as possible, but no simpler. Right? So he captured the trade-off between minimum description length, simplicity of the representation, and the accuracy. Right? That's Einstein's razor. So one more result returns here to your Gricean sort of thing. So in this Bayesian change detection, there are actually two objective elements that ought to enter into the decision whether there's been a change. One is the Bayes factor, which depends upon the sequence of green and red circles. That is, basically depends upon whether there are more green circles toward one end of the sequence versus toward the other. Right? That's fairly obvious. Right? If there are a lot of green circles here and not many here, then that favors the change model, and the Bayes factor captures that part of it. But another less obvious part of it is the so-called prior odds, namely how long is the sequence that you're looking at. If you know that changes occur roughly once every 200 trials, and you're looking at a sequence 1,000 long, basically I would say don't show me the data, there's been a change. Because the prior odds, which is this is a perfectly objective fact, right? This is not a subjective fact. The prior odds that there's been if changes occur on average every 200 trials, the prior odds that there's a change in a sequence of 200 trials, this is completely independent of the pattern of circles within the sequence, right? This is just, hey, in sequences that long, there are almost always changes. Right? So the really good change detection algorithm would take into account both the prior odds and the Bayes factor and multiply the two of them in order to get the posterior odds. Our model, I didn't show this clearly, but our model is also estimating the change. Every time it records a change, it updates its estimate of the rate at which changes are to be encountered. And the result is that if it starts out thinking changes are too frequent, it detects changes more frequently than it should. But because it's adjusting its estimate, the rate at which it detects changes goes down. And this is data from an actual subject. This is the cumulative record of the number of changes that the subject detected. And as you see early on the subject, this is steeper and then shallower up here. So early on this subject, and 9 out of the 10 subjects looked like this. Early on this subject was detecting changes more often than they were later on. And their rate later on was much closer to the true rate of change than was the rate early on. So they did have prior.
Even at the end, they're overestimating the rate of change.
It varied between subjects. Most of them were indeed overestimating. One was basically spot on. But yes, even at the end. So you can capture this in our model just by putting a fairly strong prior on how frequent, captures your Gricean idea that, well, they wouldn't be telling me about these changes if they didn't happen pretty often. Right? So the model naturally captures that. I forgot to mention, Frank, the second free parameter is the decision criterion on the Bayesian change detection. There's only two. All those predictions that you saw are just with two free parameters. This is already obvious. Does anybody care about objective priors? Anyway, for those who do, the priors are not free parameters because they're so-called objective priors. They're what are called Jeffreys priors. So they're determined by purely mathematical considerations and not by the data. And here's the model's distribution of step widths and step heights. It's not perfect. I have a slide in which I put the subjects alongside this, and I'm a little disappointed in myself that I didn't show that to you. But anyway, this doesn't perfectly capture. There are some differences in what the model does, but it gets the marginal distributions basically right, and it's certainly a much closer approximation to the empirically observed distribution, joint distribution, than the other models.
One observation, the step width was more of a skewed distribution.
Yes.
Later, right?
Yes. No,
It
this.
wasn't a skewed. This is a skewed.
That's exactly right. Ooh, got a sharp eye. Yeah. So the density of plots is more even out to longer step widths, and also the step widths are more concentrated. The subject's marginal distribution looks something like that. Okay, it doesn't. The peak isn't here.
Is there a difference in how well it fits width versus height?
I haven't really tested that. You can't test that. I'm tossing together the data from all 10 subjects here, so you couldn't. I haven't tested that. But, you know, keep in mind, you're trying to fit a number of incommensurable aspects of the subject's performance, so it's not clear what's the point of. You get the drift to the 2p. So, as usual, this won't come to any surprise to Frank at least. I believe that we can generalize beyond this, just the perception of probability here. I think that we're looking at some general truths here. And I'd like to suggest that this, if it ain't broke, don't fix it, is actually quite a general property of sensory perceptual processes. It makes sense because for straightforward computational reasons, it's much easier to decide whether it's broke than it is to decide why it's broke. So there's no point in wasting your time trying to decide why it's broke if it ain't broke. And that's quite generally the case. Second thoughts. This is not very well suited to this audience, this talk, but the second thoughts are, now we're getting into, second thoughts, of course, occur all the time in linguistics, right? But I think most of us would recognize that second thoughts actually occur all the time in practically all of our representations. I'm reminded of the Ford Maddox Ford's The Good Soldier, in which and there are other novels like this, in which the whole point of the novel is sort of, in the second half of the novel, you realize that what you thought was going on in the first half of the novel was completely wrong, right? And you share this with the protagonist, right? The protagonist realizes that the story he had about his marriage during the first half was actually, in the light of what happened later, was a completely erroneous story. So the point of this model is this should be the case, because in fact the future does have information about the past. That is, the circles you have not yet seen are in fact relevant to deciding whether there has been a change or not, so that you ought to have second thoughts. And of course the same thing occurs in language. So I want to thank my collaborators again, and thank you for your patience.
In our complex society, people are not very good at estimating risks, right?
Estimating.
Risks of taking an airplane or whatever.
Yes, well.
So how do you, it seems quite different from what you found here. Is it because the probabilities are very small? What, how do you explain?
Yeah, the honest answer is I don't know. A somewhat more, I'm not sure informative, a somewhat more interesting answer is that a lot of risk estimation is not direct estimation of probability, it's estimation of likelihood, relative likelihood. It's estimation of what's sometimes called reverse probability. So which outcome is more likely, which state of the world, I'm sorry, not which outcome. Direct estimation is which outcome is more probable. Reverse probability likelihood is which state of the world is more probable or likely given some data. A lot of the experimental literature on probability estimation is actually estimation of relative likelihood, that is, which state of the world is more likely. And as Brown and Beach pointed out back in the 60s, they already called attention to the fact that the direct estimation of probability is usually accurate. And in that same review, they said that the reverse probability is usually much too conservative. People underestimate the relative likelihood. And that summary of the results has held up very well. That continues to be true. Now, that is nothing like a complete answer to your question, but I think it's relevant, is all I can say. Yes?
Your subjects were very impressive in how they performed. Could you describe who they were?
Basically, they were people, so they were mostly graduate students or people with too much time on their hands because they were quite a grab bag of, they were different nationalities. They ranged in age from their late teens into their 30s. They were people you could get to come back for. Actually, the sessions, although there are 1,000 trials, subjects clicked through. It was self-paced, and they went quite fast. So they were looking at a new circle about every 2 seconds. So it only took about half an hour to complete one of these 1,000 trial sessions. Nonetheless, some subjects didn't come back, anyone who's run human subjects and so on. So it was basically people you grabbed out of the hallway, my postdoc. It wasn't a random sample of any definable population and so on. But the results, most psychophysicists like myself only like to work with things where basically you always get the same result. Every subject is a replication. And that was true here. Every result that I have talked about was seen in every one of the 10 subjects. So we don't, this isn't social psychology, this is psychophysics, right? We run a subject and we say, okay, here's the truth for that subject. Now let's see if the same truth applies to the next subject. That's why we get so many trials from each subject. So, 10 subjects picked. It was at a university, so we were they were almost certainly better educated than many, but it's an incredibly boring task. My belief, but I haven't put it to the test, is that almost any subject grabbed off the street would look roughly like this, but I haven't really put that to the test. Yes?
A two-part question. I'm wondering if it seems that there's something this is available in your data if you've ever thought about it, but for an inherent bias to commit the hot hand fallacy, or conversely maybe a gambler's fallacy, is there any way you can see that in your data? And so there's ideas that there's possible that this is something that works across domains. And the second part of my question is, do you expect domain-specific effects? So depending on the nature of the stimuli, maybe you would see different sorts of patterns depending on the relative errors.
So the answer is, do we expect them? No. But have we looked to see whether our expectations are conform to reality? No. I mean, I would be surprised and disappointed if this turned out to be in any way dependent on the materials, but I haven't tested it. Coming to the gambler's fallacy, I think maybe we have something to say about the gambler's fallacy, and it goes back to this question of the prior odds. So the gambler's fallacy is when you're looking at a coin flip process and you think, well, there have been a lot of lousy flips, but now the luck is turning my way, right? So, of course, that's a fallacy, assuming that, as was asked at the beginning, is that the flips are independent, right? Because the coin has no memory of how many times it's been flipped. What isn't a fallacy is I've been down for 20 trials. Maybe my luck has changed. I just haven't seen the consequences of the change. That gets back to the prior odds. So if you believe that you're, as I think most people do, that the hot hand exists and that luck does change, then it is not erroneous reasoning to say, well, if I've had a long stretch of bad luck, the odds have increased that my luck already has changed. Not that it will change, but that it has changed a few trials back, and I just haven't seen the beneficent effects of that yet. That's not a fallacy. That's related to the prior odds. So maybe we stick that in. This is in press in the Psychological Review, and we put that in there. Yes?
So maybe linking Roberto's comment about how people are bad at estimating real probabilities of hazards, for example, and Greg's comment about domain specificity. I think you said you want it to hold and you expect it to hold across domains.
Yeah.
But one aspect that isn't in the probability estimation is the cost of the errors, right? So
that's absolutely the case.
presumably the reason that people grossly overestimate the risk of flying in airplanes, for example, at least one component in there,
Sure.
is that there's an asymmetry in the cost of the errors.
Yeah, absolutely.
And you could,
But that's, of course, absolutely rational. If that's all that's going on, that's completely rational. That is.
But so here's my point, which is that while staying in the abstract world of circles, the caveat that recruiting people with too much time on their hands is not easy to do.
Right.
You could introduce that by introducing an asymmetry in the. You incentivize the choices, right? So.
Yeah.
Being right about green turning to red is different than being right about red turning to green or something like that. And then you should actually see a secondary effect independent on top of, but independent of the one that you don't.
Yes, you absolutely should. And depending on the magnitude of the effect, it is entirely rational, right? We have done something a little bit in the spirit of that, in that we have another task which I haven't described, which we run with both mice and humans. I was telling Alan about it last night. We run essentially the identical task with both mice and humans. And it's a task that combines uncertainty about how much time has elapsed with the probability of various outcomes. And so basically you're making a decision. It's like you're at a traffic light, and you know it's been red for quite a while, and the guy behind you is starting to honk. And you know there is some probability that traffic lights are broken, right? If you don't go through this light sooner or later, the guy behind you is going to get turned homicidal, right? So, so you're weighing, you know, does a traffic light ever last this long, right? Against, because of course you don't have a stopwatch on it, right? So you've got uncertainty about how long the light, you've actually been sitting there, plus some estimate of the probability that the light is broken, and so on. And your decision is a joint function of your uncertainty, of the temporal uncertainty. Well, we've got a task that captures exactly that. The mouse or the human, at each trial, they're either going to get a pellet on this side at a short latency or a pellet at this side on a long latency, but they have no way of telling at the beginning of the trial. The irrational thing to do, which both the mice, well, we tell the humans, and the mice learn it very quickly, is on every trial they go first to the short side and they poke there until either they get their pellet or they judge that more than 4 seconds have elapsed, at which point they leave and they go to the long sign. All right? Now, we put the goalpost, so this is a temporal goalpost sort of thing, right? You know, the switch should be positioned between 4 seconds and 8 seconds, which it usually is. Now, suppose we change the probabilities of short trials. Okay? Suppose short trials are actually very unlikely. What should the rational observer do? Well, they should shift their entire distribution of switches toward the short end, right? Because the average risk, which is the product of the probability of a short trial.
You said the short end, shouldn't they shift towards the long end? Because
No, I
short trials are-
think maybe I lost track. I said short trials are unlikely, didn't I?
Yeah.
Yeah. Okay. So when short trials are unlikely, long trials are likely, right? Think about it as soccer. So when the goalie is guarding the long side, you should aim for the short side of the goal, right? The goalie guarding the long side is the equivalent to long trials are frequent, right? And short trials are infrequent. If I had a whiteboard, you could just imagine a normal distribution, right? And you've got these two goalposts, right? And now the risk that you run is the tail, the part of the distribution that lies outside the goalpost, right? But it has to be weighted by the probability that of the left or the right goalpost, all right? So if this is a low probability event, then the tail that lies on the short side gets low weight, whereas the high probability over here, that tail gets higher weight, all right? And the rational observer will switch their distribution so that the weighted tails are equal. And that means you're going to switch your distribution away from the long side towards the short side. And similarly, when we make the short trials very probable, think of it this way. If the short trials are very probable, then if you leave prematurely, you're running a substantial risk of losing your pellet. Right? So you shouldn't leave prematurely, right? Which means you should shift your distribution to the long side. Both mice and humans do that very well and surprisingly accurately. In fact, you basically can't tell the difference between the human data and the mouse data. Right? So they are jointly evaluating their temporal uncertainty and the relative risk of doing this versus doing that. Art. Hi. Question? No question. Yes.
So, we're not particularly interested in the subjects, we're only interested in, we're mostly interested in what goes on in the rest of the world, not outside the psych laboratory.
Yes.
So, talk to us a little bit about what kinds of real world, real non-weird people things that this applies to and how it applies to. So I live in a world of foraging and fishing and gathering and so forth and so on, hunting. What decisions does this tell us about, and what is missing from this model that would be really important in those real world settings?
So Bernoulli probability is the most common stochastic process that we encounter, right? At least. I haven't done a survey of this. I mean, keep in mind, Bernoulli probability is intimately tied to decision making in general because of the binary character of it, right? It's not the only stochastic process, certainly, that we encounter, but I would argue, on the basis of pure gut feeling, I can't cite any survey data, but that Bernoulli processes are the most common process, and they enter into every kind of decision making. I'm giving you a very, I'm not giving you a particulars answer here, because I'd have to sit here and start. The traffic light example is, of course, one example, but leaving for the airport. Okay, most marriages I know come close to faltering on the issue of when you should leave for the airport, right? So what's at issue here? Well, you could leave later and run the risk of missing your plane, right? This is a Bernoulli, either you miss your plane or you don't miss your plane, right? And then if you leave early, then you spend time. These days now that they have Wi-Fi at the airport, I don't mind. It's produced marital harmony. I'm willing to leave earlier because I can do my email at the airport. But it used to be I couldn't stand sitting around the airport just twiddling my thumbs waiting for the plane. Okay, so decisions about when to leave against a Bernoulli outcome are the stuff of everyday life, right? You're going to go pick your kid up at school, you know, preschool. At least the preschool our kid went to. If you arrived after 6 o'clock, you paid some horrendous.
These are very artificial situations in the history of human beings in which there are clocks, and these are weird people. These
Okay, so you go out to run. You go out to hunt antelope.
Yeah. Okay.
Okay. Yeah. You're either going to come back with an antelope or you're not, right? It's a Bernoulli outcome.
What probabilities would you be estimating that would change abruptly from one probability to another?
Probability of catching an antelope, right? Are they migrating? You know, if you're right, if they're migrating past your front door, all you got to do is step out and fire, right? But if they're 200 miles away, then the antelope are very thin in the ground, right?
Have you thought about how it mixes with optimal foraging theory or something like that? I think that's
Well,
kind of
optimal foraging theory presupposes that you have a correct estimate of the probabilities. So, I mean, in foraging, you're out looking for tubers. Got to be careful here about my examples. Are you going to find a tuber or not, right? There aren't that many tubers out there in the desert.
It does not change. The probability of a tuber being in a particular plot of land doesn't change abruptly from one probability to another at a given point in time.
Yeah, but there are, so
Well,
resources are patchily distributed, right?
If we're about to run a version of the experiment in which the changes are gradual, if that. No, I understand.
I'm not saying there aren't many.
No.
Rhetorically, I'm not saying that this doesn't apply.
Yeah.
I'm saying when we try to apply this to
Yeah.
real-world ecological things that the humans and
Right.
animals face,
Right.
what else do we suddenly discover is important about the real world that this model in the lab is,
Well,
is
as
leaving
was
out?
brought out earlier, of course, we're not doing outcome weighting, right? Outcome weighting is, of course, hugely important in the real world, right? If you're running away from the cops and you're contemplating jumping from one roof up to another, this is a New York example. Well, how long you're going to be in for if they catch you, and how big is the gap you contemplate jumping, and so on, right? There's some pretty serious outcome weighting going on here.
But the building distance isn't changing at random times.
Which
Depending which way you run.
you don't know the roofs of New York. Usually these chases involve more than one jump, right? And different jumps involve different gaps.
That's not modeled by your case, because your case is
What's modeled by my case is the Bernoulli part of it. So the reason the Bernoulli is so common is because whenever you apply a cut on a normal distribution, for example, you end up with a Bernoulli process, right? So that's exactly what's going on here. Your jump distances are presumably more or less normally distributed, right? But the outcomes has a very strong cut in it, right? You either make the next building or you don't make the next building, and that is a Bernoulli probability.
You're going fishing. You've got a bunch of lakes or ponds you can
Yes,
fish in.
right.
It's season to season. It's true you don't have to change suddenly in time, but the basic essence of the problem is the same.
Yeah.
You decide this season are the probabilities different from last
Or
season.
even day to day. I mean, I'm a lousy fisherman. I have no patience, but I've done enough fishing to know, gee, I went there this morning and I caught 3 trout in half an hour. I went there in the afternoon and I didn't get a single strike. From the standpoint of, the way in which we sample the world itself is by and large continuous, but we sample it discretely, right? So the fishing example shows, right? Yes, Art?
Plenty of social examples of judging the probability that your wife is going to agree with you.
Well, if I ask her out for a date, will she accept, right? I mean, boy, if your adolescence was anything like mine, this was certainly a probability that I spent some time contemplating, and it was...
Did those probabilities for a given person change at discrete points where there was something?
Well, we're getting into your field here, but I think these probabilities are to some extent hormonally dependent, among other things. Yeah, they change. I would say most probabilities change. Do they change abruptly? Oh, no, that's much more difficult. That's why we're going to run the continuous. We're very interested to know whether when the changes are continuous, particularly if they're aperiodic but continuous, are they showing these step-like things, or are they smoothly tracking? And then if we make them perfectly predictable, sinusoidal, will they learn that higher order structure and show smooth tracking? We don't know the answer to that, but stay tuned. And once I get past the IRB, which is always the biggest obstacle, and it's crazy, you know. You're just asking people how many green circles do you think there are, and you have to jump through all these hoops. But anyway, well, sooner or later we'll know. 1:30, I think that's the witching hour, right?